Okay, this is then copied in video number 30, and in the video number 31 I want to spend some minutes in the delay time block. What is this? Delay time block. We have no real operation amplifier circuit, but we can define the behavior of a delay time block just with a step response. Definition, where is step response? You can see what I mean, what the delay is. The step response is nothing else. Let's just show the unit step response. There is 0, here's time 0, the input switches, but the output sends this step function just a delay time later. This is a TD delay time. With only one parameter, TD, and you see any signal, not only the step, any signal is just delayed with exactly this time. Application examples. Application examples. In control systems, we have often delays. For example, heating system with material transport, with water transport, with material transport. Then we have a delay. Very simple. Yeah. If the heater starts heating, the water maybe will be at once warm, but if you want to have the warm water in the room, the pump has to transport the water into the room, and this difference, the time between water in the heater and water in the room, is just a delay time. Before the hot water is not reaching the room cannot be heated. Yeah? Material transport is causing delays, but there is another big effect which causes delays, especially in digital systems. Yeah? In digital systems, the calculation time, for example, is a delay. Yeah? Conversion and calculation times cause the delays. Calculation times, calculation and conversions, and the simple step of sampling of a signal. So conversion of an ADC analog signal into a digital signal caused a delay. Yeah? Calculation and conversion caused delays. The problem with the delay is we cannot compensate a delay. It's impossible to compensate a delay. And we need a prophetic block where the output comes before the input comes. So this is not possible, so delays should be avoided in closed loop systems. I will later explain this. Negative phases for a delay caused quickly instability and slow loop reactions. Delay time block is defined with the step response. We can just check the symbol. The symbol is exactly that thing. Some people like to give a delay time block also K, but normally the K is 1. I think this is otherwise you add a P block in front or after a delay time block, then you have a different K. The symbol is delayed step response, and the only parameter you have is TD. The question is, can we write down the transfer function in polynomial form? Answer is no, it is impossible. A delay time block cannot be expressed in the polynomial form. but the Laplace transformation gives the answer how the transfer function can be written, because we know maybe the rule of delay, the delay rule in Laplace transformation. If in time domain a signal is delayed, in frequency domain the signal is multiplied with the exponential function e to the power of negative complex frequency p times the delay time. That is the shifting operator, we can say. Yeah, Laplace shifting theorem, shifting operator. If we shift delay a time signal with Td in frequency domain, we have to multiply the frequency function with e to the power of minus p times Td. The magnitude of this function is the magnitude of e to the power of negative j omega Td. And if the exponent is pure imaginary, then we can convert with Euler and a cosine j sine function, and the magnitude of this is 1. So the magnitude is 1. Delay time block doesn't change amplitudes of signals, doesn't change amplitudes of sinusoidal signals. There is only a phase phi. The phi is nothing else than the part beneath the j in the exponent of e, because this is a phasor in the frequency response curve. So the phase is negative omega Td, always negative. But of course now you have to be careful. This is the radian value. Yeah, if Td is 1 second, omega 1/2. This is -1, that is not degrees, that is just in pi in rad. If you want to have the degree value, phi in degree value, you have to correct this by the conversion factor 180 degrees divided by pi. Then you have this in degrees. Now the phase of this negative phase of this delay time block can be expressed in rad or in degrees. Because we need the phase value in degree, we have to work with this equation, omega times Td times 180 divided by pi. The phase curve itself looks simple in Bode plot. Now strange, you will just wonder why is this possible. The phase here is linear, but in a logarithmic scaling that is not a straight line curve. This is an exponential curve. So in Bode plot, this phase goes down, negative, yeah, and we can mark 2 points, 2 typical points. One point is where the value reach negative 180, because then the sinusoidal signal at this point, we call this omega 180, because the sinusoidal signal is inverted. Yeah, if you shift the sinusoidal signal by -180, then it's the same as if you have added an inverter. And a closed loop system with an inverted sinusoidal signal moves from a negative feedback into a positive feedback. So if the amplitude here is large enough at this frequency, then your loop becomes unstable. That's the problem with the delay time block, could cause instability. How large is omega 180? Omega 180 is Z omega, where phi is negative 180. And so you see 180, negative 180 Td times 180 over pi is negative 180. And you can solve this easily for my inverting frequency point, we can say. This is true there were omega 180 times TD over pi is 1, or omega index 180 is pi divided by TD. So this is, the frequency here is like pi divided by TD. And some people also want to know where is the 1 over TD point, how large is the phase here. This is the phi, we can say phi TD value at corner frequency. In PT1 this is a corner frequency, of course here is no corner, but sometimes people like to know the phi TD value, positive. The definition of this point is positive value, PTD, of course, phi TD is of course negative, is at the frequency where omega is 1 over TD, omega is 1 over TD times TD times 180 degrees divided by pi. This then is independent of TD, is negative 180 divided by pi, and this value is, I have to calculate this quickly, is negative 57.30 degrees. Yeah, so this is the phase value at 1 over TD. Sometimes this is useful, or you have to work with the inverting frequency. Yeah, inverting frequency. Okay. Yes. Some words. If you have a delay time log in my simulation program, you can, of course, present the Bode plot with a delay time log. This phase curve looks strange in my simulation program. I should just show you this. Okay, if you start it and switch to English menu point, take this delay time log, put it here. Block gain can be changed, but I leave at 1. Time constant, say 100 millisecond. Okay. To draw a Bode plot, you need at least one branch to define what is input and what is output. If you click now on the Bode plot function point, then you can see the following curve. The input is, of course, the 71 open input. Output, we have only one block, no problem. Starting omega frequency is 0.1. Just recalculate only magnitude, which is simple. Yeah, you see 0 dB constant line. Here the auto scaling program has some some problems, so forget the magnitude. The phase curve is much more interesting, so delete this curve and recalc the phase curve. If you want to have the logarithmic scaling here, press on this point. Note that in my simulation program, this is not the logarithmic value of omega, but is omega itself. This axis is the omega axis, so we have here omega 1, 10, omega 100, omega 1000, and so on. Now look what happens here. We have here a phase shifting. In our equation, there is no phase shifting. Yeah? Here we make a phase shifting because this program automatically makes that what we call phase phase wrapping. This word comes not into my brain. Phase wrapping, that means all values which are deeper than minus 180, here's the phase scaling, here's minus 180 at this point, is then shifted with 360 degree to positive values. So negative minus 180 is the same as positive 180 because the information in this diagram is the information about the phase shift of the sinusoidal signal. And if you shift a sinusoidal signal by 360 degree positive or negative, then the sinusoidal signal cannot be differentiated to the original one. So a shifting of 360 degree is unimportant for a sinusoidal signal. So you see here is this shifting, and now the phase values are larger and larger negative, and the phase wrapping method is just done more often. Note that the point number of Bode plot in this simulation program is fixed to 256, not more. Step response is calculated with 512 points. Bode plots are drawn with 256 points. It is just not changeable in this program. Normally this is enough points. Okay, so this is a delay time block. Look, there is also a point of polar plot. If you click this, then we recalculate this. A nice curve. That's a nice curve. Okay, strange in this case because I expect a circle. Why is this not a circle? I think I know this. Because of 2 less points. Because of 2 less points. So if I start with the radiant frequency a little bit more earlier, maybe this will be better. So if I make this small enough, then you will see then the polar plot of my delay time block is the unit circle. Note here we have 0 axis point here, a negative one here, positive one here, positive one here in the top, negative one here. So this is the unit circle if the scaling would be same centimeters for the same numbers. Okay. So sometimes simulation programs must be used carefully together with a good thinking. Okay, so far I close the discussion with the delay time block and start with the last discussion point, which is a PT2. So this video ends here, and this is video, which number we have now? Wait for the number. That is video 31.